Hey guys, I hope you had a great week. Today we're going to be going over Chapter 14, End of Chapter Example Problems, and taking a look at the two-factor independent measures analysis of variance with main effects and interactions. Our main effects and interactions will have three distinct hypotheses. The first will account for the differences that are produced by factor A. The second are the differences that are produced by factor B, and these are acting independently. And then the third will be the differences produced by the two factors acting together. In our first example, we are given results from an independent measures two-factor study with n equals 100 participants in each treatment condition. We are asked to calculate a two-factor ANOVA with an alpha level of 0.05 to evaluate the main effects and the interaction. First, we'll calculate the total variability by taking the sum of x squared and subtracting g squared divided by n, and we get a value of 2,800. Next, we'll calculate the degrees of freedom total by subtracting 1 from the total amount of participants in the study. Next, we'll calculate the degrees of freedom within by adding up the degrees of freedom within each treatment. Since each treatment has 100 participants, n minus 1, which is our degrees of freedom, will be 99. Since we have 4 treatments, we'll multiply 99 by 4, and we come to a value of 396. In order to calculate the within treatments variability, we will add the sum of square deviations of each treatment. In this case, we will come up with a value of 1,800. The between treatments variability will be the total variability minus the within treatments variability, and the degrees of freedom will be the number of treatments minus 1. In this case is 3. SSA calculates the between treatments variance for factor A. We will add up the total scores for each row of factor A. Then we will square those scores and divide them by the number of participants in that row of treatments. Then we'll add them together and subtract our grand total squared divided by the number of participants in the entire study. In this example, we come up with a value of 100. To calculate the between treatments variance for factor B, we'll add up the total scores for each column of treatments this time, square them, and divide them by the total number of participants for that column. Then we'll subtract our grand total of scores squared divided by the number of participants in the entire study. We come up with a value of 900. Now we'll calculate the variance for the A by B interaction. We'll start with our between treatments variability and subtract SSA and SSB. In this case, we reach a value of 0, which means there won't likely be a difference accounted for by the interaction. The degrees of freedom for A is the number of rows minus 1. The degrees of freedom for B is the number of columns minus 1. And the degrees of freedom for the A by B interaction is the degrees of freedom for between treatments minus A minus B. Our mean squares are calculated by dividing the sum of square deviations by degrees of freedom. And the F value for each factor is its own mean square divided by mean squares within. Treatments. Once we find all of our F ratios, we have to determine their significance by finding our critical F. We'll use the degrees of freedom for each treatment and the interaction as the numerator, and the degrees of freedom within for our denominator. We'll move our slider over to determine the correct alpha level, and we'll see our critical F ratio. And if our F ratio is in the tail, it's significant. If it's in the body, it's not significant. In this case, since I made up the numbers, there is no critical F for 396. So we're going to pretend like it's 44.113. And we'll see that our F ratio of A, factor A, is 21.97. So it's in the body and it's not significant. But our F ratio for factor B is in the far tail, so that one would be significant. Now we'll measure effect size by computing the value for eta squared for each factor and the interaction. The formula for this is to take the sum of squared deviations for the factor and dividing it by the total minus the sum of squared deviations for the other factor and the interaction. This allows you to isolate the percentage of variance that is explained by each treatment individually. Our next question provides us with a partially filled out summary table of the results from a 2-factor study with 3 levels of factor A and 3 levels of factor B, using a separate sample of n equals 10 participants in each treatment condition. In order to fill in the missing values, we're going to use the same equations, just in a slightly different order. First, we'll look at the matrix of our 2-factor study and see that there are 3 columns and 3 rows, which give us 9 treatment conditions. We'll first calculate our total number of participants by taking the number of participants in each condition and multiplying it by 9, which is our number of conditions. Then we'll subtract 1 to find our total degrees of freedom. And to find our degrees of freedom between, we'll take our number of treatment conditions and subtract 1. Our degrees of freedom within is the sum of the degrees of freedom in each treatment, which would be 9 times 9, or you can just take the total degrees of freedom and subtract the degrees of freedom between. The degrees of freedom for factor B is the number of columns minus 1. Here we have 3 columns, minus 1 gives us 2. Likewise, our degrees of freedom for factor A is the number of rows minus 1, which will also be 2. The degrees of freedom for the interaction is the degrees of freedom between minus the degrees of freedom for factor A minus the degrees of freedom for factor B. Since we already have our sum of squared deviations between treatments, we're going to move our formula around and solve for the sum of squared deviations within treatments. Since we have the sum of squares within and the degrees of freedom within, we can calculate our mean square within treatments. This will allow us to calculate the F ratio for factor A by taking the mean square of factor A and dividing the mean square within treatments. We can use the mean squares formula to find the sum of squared deviations for factor A by plugging in the mean squares for factor A and the degrees of freedom for factor A, which we already have. We'll multiply each side by 2 and find a sum of squared deviations for factor A is 36. Since we know the F ratio for our interaction and the mean square within, we can use these numbers to solve for the mean square of the interaction. We'll multiply each side by 3 to get rid of our denominator and find a mean square of 21. Then we can use that mean square to find the sum of square deviations for the A by B interaction. We'll plug in our mean square for the interaction and our degrees of freedom for the interaction, multiply each side by 4 to get rid of our denominator, and find a sum of square deviations for the interaction of 84. Since we know all of our sum of square deviations except for the one for factor B, we can move our formula around a little bit to solve for the sum of square deviations for factor B. We'll add SSB to each side and subtract the sum of square deviations for the interaction. We'll find that SSB is equal to sum of square deviations between minus sum of squares for A minus the sum of squares for the A by B interaction. When we plug our numbers in and solve for SSB, we come up with a value of 24. This will allow us to calculate our mean square of B by taking 24 and dividing it by the degrees of freedom, which is 2. Then we can calculate our F ratio for B, which is 12 divided by 3 and equals 4. In our next example problem, we are given the raw data from a research study on the effects of small group tutoring with and without validated classroom instruction on at-risk students' math problem solving. We are asked to calculate a two-factor ANOVA with an alpha of 0.05 to evaluate the significance of the main effects and the interaction. First, we'll have to find our sum of scores, our means, our sum of squared deviations for each treatment condition, as well as our grand total of scores, our grand total of squared deviations, and the total number of participants in the entire study. We'll start by finding the sum of scores for the A1-B1 quadrant, and then we'll divide our sum of scores by the number of scores in that quadrant to find the mean. In this case, it is 3.25. We'll find our sum of square deviations with our sum of square deviations formula, which is the sum of x squared minus the sum of x squared divided by n. We'll square each of our scores individually and add them up to find the sum of x squared, and t is our sum of x value, so we'll square that and divide it by n, and come up with a value of 10.75. Then we'll find the sum of scores, the mean, and the sum of square deviations for the A1-B2 quadrant. We'll perform the same calculations for the A2-B1 quadrants and the A2-B2 quadrant. Now we can find our grand total, which is the sum of all of our t values, and equals 103. The sum of x squared is the sum of the sum of x squared for each treatment condition, and equals 835. Our capital N is the sum of the participants in each treatment condition and equals 16. We'll use these numbers to calculate our total variability, which is the sum of x squared minus g squared divided by n, and equals 171.94. Our total degrees of freedom is n minus 1, which equals 15, and our degrees of freedom between is the number of treatment conditions minus 1, which equals 3. We can use these two numbers to determine degrees of freedom within, or just add up the degrees of freedom of each treatment, which equals 12. To calculate the variability within, we'll add the sum of squares for each treatment condition, and use this, as well as the total variability, to calculate the between treatments variability, or SS between. To calculate the sum of squares for factor A, we'll have to add up our t-scores in each row, square them, divide them by the number of participants for that treatment, add the rows together, and then subtract our grand total squared divided by the total number of participants. And we get a value of 39.06. To calculate the sum of squares for factor B, we'll have to add together the total scores from each column, square them, divide them by the number of participants in each column, add them together, and subtract g squared divided by the total number of participants. To calculate the sum of squares for the interaction, we'll take our between treatments variability and subtract our sum of squares for factor A and our sum of squares for factor B. And our degrees of freedom for factor A is the number of rows, which is 2, 1, 2, minus 1, which equals 1. Our degrees of freedom for factor B is the number of columns, minus 1, which is also 2, minus 1, which equals 1. The degrees of freedom for the interaction is the degrees of freedom between treatments minus the degrees of freedom for factor A minus the degrees of freedom for factor B, which also equals 1. Our mean squares should be relatively easy to calculate because all of our denominators are 1, so we'll copy our sum of squares over into our mean squares. Then we'll calculate our mean squares within and use that to determine our F ratios. To calculate our F ratio, we'll take the mean square of our treatment and divide it by the mean square within. Then we'll find our critical F ratio by using the degrees of freedom for the treatment as the numerator and the degrees of freedom within as the denominator. Once we set our alpha level at 0.05, we can take a look at our F values and see that they would be significant if they were in the tail and not significant if they're in the body. We can see that our F ratios for both treatment A and B are in the tails, but our F ratio for the interaction is not, so it would not have a significant effect. Well, I hope these examples have helped you with your calculations for the Chapter 14 end of chapter questions, and hope to see you next time. Take care.